Ever get a great score one run and a terrible score the next with the same code? Let's fix the split so your results stop swinging randomly. You run experiments and the numbers jump around. Often the root cause is not the model, but how you split the data. By the end of this video, you will understand how to split imbalanced data so the minority class is not lost and your evaluation is honest. I'm Professor Pi, teaching AI foundations with simple Python. To make the problem concrete, we will work with a tiny imbalanced binary dataset and walk through what happens with a naive split. Then, apply stratified splitting methods and a baseline evaluation. This shows why stratification matters before you tune models. Now, let's create that tiny dataset and check its imbalance. This snippet creates a tiny imbalanced binary dataset and reports its class ratio. We use NumPy to build X as a simple feature column and Y with 3 positive labels followed by many negatives, making the minority class 10%. The variable R computes the fraction of ones in Y, which is a quick, reliable way to quantify imbalance. Keeping this setup deterministic ensures later splits and metrics are reproducible. If you increase the number of ones, the ratio rises and stratification becomes easier. Reducing it makes preserving ratios harder. Seeing minority ratio equals 0.10 confirms the class imbalance we must preserve in all splits. Next, we will show what happens when you split without caring about class proportions. This snippet uses scikit-learn's train test split without stratification to show how a rare class can vanish. We split with test size set to 0.2 and shuffle disabled to mimic ordered data, which pushes all minority samples into the training block. The variable C counts positive labels in the test set and exposes when a class disappears. Without Stratified, small test sets or ordered inputs can easily end up missing rare labels. Increasing test size can help, but it's unreliable compared to proper stratification. The printed naive test minority equals 0 shows the evaluation split lost the minority class entirely. Now, let's fix that by forcing the split to respect label ratios. This snippet applies scikit-learn StratifiedShuffleSplit to preserve class ratios in a single train test split. We create SSS with a fixed random state for reproducibility and ask it to split X and Y while maintaining label proportions. The variables IDXTR and IDXTE are index arrays that select balanced train and test subsets. We then count positives in the test selection to verify the minority is represented. Increasing test size allocates more minority samples to the test set. Decreasing it too far can make stratification infeasible. The printed strat test minority equals 1 confirms the rare class survives in the test split. With single splits fixed, you often want cross-validation that also keeps the rare class visible in every fold. This snippet checks scikit-learn StratifiedKFold to ensure each fold's test split keeps the minority class present. We configure 3 splits with shuffling and a fixed seed for stable, repeatable partitions. The list comprehension iterations over each fold's test indices and counts how many positive labels appear. With 3 positives total, stratification spreads them evenly, yielding 1 per fold. If n splits exceeds the minority count, StratifiedKFold cannot allocate at least 1 minority per fold and will fail. The printed kfold minorities equals 111 shows every fold's test set includes the rare class. Finally, we measure a simple baseline to show why stratification matters for evaluation. This snippet builds a simple baseline using scikit-learn's DummyClassifier and evaluates it with balanced accuracy on the stratified split. The classifier predicts the majority label learned from y-idxtr, providing a yardstick for improvement. We then compute balanced accuracy score on the stratified test indices, which averages recall across classes to avoid majority bias. A constant majority predictor scores 0.50 here because it gets all negatives right and all positives wrong. On the earlier naive test with no positives, plain accuracy would have been misleadingly perfect. The printed baseline BAL ACC equals 0.50 flags that the baseline ignores the minority class. Recap what it is. Stratified splitting keeps class proportions the same between train and test or across folds. When to use it? Whenever you have class imbalance and you need reliable evaluation of minority performance. One caveat: stratification cannot create samples. If the minority has fewer examples than folds, you must reduce folds or collect more data. Next step: increase the number of folds while keeping n splits no larger than the minority count, and evaluate balanced accuracy across folds to see variance. That will give you a more robust picture of model behavior on rare labels. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.